Welcome back, dear students. So in the last class we have derived the air standard efficiency of Otto cycle, which was the working cycle of petrol engines. So in this session we will try to derive the air standard efficiency of diesel cycle, so which is the working cycle of most of the low speed diesel engines. Now first we have to identify what is the difference between this Otto cycle and diesel cycle, and this derivation will be a little bit complicated compared to Otto cycle. So first we have to identify the four process, just like Otto cycle. What will be the first process? Is there any difference in first process of Otto cycle and diesel cycle? No. It starts by compression. So the first process will be from state 1 to 2. That will be reversible adiabatic compression. So that is same as Otto cycle. So Otto cycle also we have reversible adiabatic compression, which is also known as isentropic compression, because when a reversible process happens adiabatically, its heat will be 0, and we have ds is equal to dq by t for reversible process. So entropy change will be 0. That means entropy is a constant, and therefore it's known as isentropic process. Then the second process is heat addition. Remember, in Otto cycle we have constant volume heat addition, but is it the same here also? No, because how a diesel engine works? A diesel engine, the heat is added by the injection of fuel by a fuel injector, not like petrol engine where we have added heat with the help of a spark plug, and that heat addition completes in very minute seconds of time. So we are considering it as constant volume, but in this case the fuel will be injected for a small period of time known as the fuel cut-off time. Hence the second process is different, that will be constant pressure heat addition. So in diesel engine, the main difference between diesel cycle and Otto cycle is the second process. So second process, instead of constant volume, here we have constant pressure heat addition. So heat is added at constant pressure. This will be with the help of a fuel injector in an actual engine. Now we have to produce the power. So we have compressed the air and we have added heat. Now we have to expand and produce some work. So our 3 to 4 will be same as that of Otto cycle, that is reversible adiabatic expansion. So this will be reversible adiabatic expansion. And last process also same, because heat is rejected at constant volume just like Otto cycle. So 4 to 1, that is our last process, that is constant volume heat rejection. So you have to be very careful, you have to understand these four processes of diesel cycle, and in this you have to remember this, only this process, the second process is entirely different compared to Otto cycle. Here it is this constant pressure, whereas in Otto cycle it is constant volume. Now what is our next step? We have defined the four processes constituting diesel cycle. Next we have to draw the PV and TS diagram just like Otto cycle. So our next step is draw the PV diagram, that is pressure volume diagram. Pressure is in the y-axis, volume is in the x-axis, and 1 to 2 is same. We have also already drawn Otto cycle, so we are not spending more time on this. So 1 to 2 is compression. As compression happens, pressure increases, volume decreases, and it is PV raised to gamma is constant. It's a hyperbolic equation. So it will be a curve in this direction. So we can mark 1 here. This is, suppose this is our 1, and this process will be like this hyperbolic curve. So this is our 1 to 2. It is same as that of Otto cycle. But here pressure will be little bit more because diesel engine normally works on higher combustion ratio. So that pressure value will be little bit higher than Otto cycle. Now what is our second process? Second process in Otto cycle, it was constant volume. It was a vertical line parallel to the y-axis because its volume was constant. But here remember volume is not constant. This is that volume. So 2 to 3 is constant pressure. So pressure remains constant. So it will be parallel to the x-axis. So here our 2 to 3 will be parallel to the x-axis. So this is our 2 to 3. And suppose this is our 3. So this will be our 3. And 3 to 4 is expansion, adiabatic expansion. So it will be the opposite direction of 1 to 2. And it should end up at a constant volume line passing through 1, because remember our last process is constant volume. So keep that in mind while drawing 4. 4 should be in this line because 4 to 1 is constant volume heat rejection. So you can draw this in this direction, another curve. So this will be our 3 to 4. This is our 4. And finally we have 4 to 1, that is constant volume heat rejection. So that is same as Otto cycle. So in this only the second process is different. All other process the shape is same. Now we can mark Q1 and Q2. The heat is added. So where is heat addition in the second process? Heat is entering in this process. So this will be our Q1. And heat rejection is 4 to 1. This will be our Q2. So this is our PV diagram. Now go for TS diagram. So we have drawn the TS diagram of Otto cycle. Similarly here also we have to draw the TS diagram. These two diagrams are very important. If you are not drawing this diagram, you may lose a considerable mark in the exam. So first process is same as that of Otto cycle. It is entropy is constant, isentropic compression, temperature increases. So that will be 1 to 2 will be here to somewhere here. So this will be a entropy, constant entropy compression. Temperature remains the increases. Temperature increases, entropy remains the same. So after that we have heat addition. Even though it is constant pressure, its shape is almost same, a logarithmic curve. Only thing is its slope will be somewhat lower than the Otto cycle. So we can draw another curve like this. So this will be our 2 to 3. So it's here we in TS diagram we may not be identify any considerable difference between Otto cycle and diesel, because constant pressure line and constant volume lines in TS diagram are almost similar, except the constant volume line, slope of constant volume line or volume curve will be more compared to slope of constant pressure line. So that is the only difference in TS diagram. So this is a pressure constant curve. Its slope will be little bit lesser compared to volume constant curve. Then 3 to 4 is expansion, again constant entropy, isentropic expansion. So it should follow this constant entropy line. So our 3 to 4 will be here, again a vertical line. So our 4 will be somewhere here. And finally 4 to 1 is constant volume heat rejection. So temperature as well as entropy decreases. And this is constant. So this is constant volume line. So that is the difference. This is a constant volume line, but this one is a constant pressure line. Shape is a logarithmic curve, same, but slope will be more for this line. So we have successfully drawn the TS diagram, and mark here also we can mark Q1 and Q2, that is heat is added in the second process, constant pressure, and heat is rejected here at constant volume. So we have drawn the PV and TS diagram. Now we can go step by step derivation. So we can start from the basic expression where we have just started in Otto cycle, that is efficiency is equal to net work by heat input. But we know from first, this is our equation 1, from first law of thermodynamics applied to a cycle. For a cycle we have this sigma q is equal to sigma w, and here also what is sigma q? Only two heat is there in between the system and surrounding, q1 and q2. q1 is entering, so we can give a positive value. q2 is leaving, so that will be a negative. So q1 minus q2, that is sigma w. So that is our 2. Now substitute 2 in 1, we will get efficiency is equal to 1 minus q2 by q1. So all these things are same as that of Otto cycle. This will be our third equation. Now just like Otto cycle, we have to identify what is q1 and q2. So what is q1? q1 is the heat entering at a constant pressure process. And what is the value for a constant pressure process? We can say the heat transfer is mCp delta T, where Cp is the specific heat at constant pressure, whereas in constant volume it will be mCv delta T. So we can write Q1 as mCp, the temperature difference, it's very positive value. So temperature is between 3 and 2, so it will be T3 minus T2. So Q1 is mCp T3 minus T2, that is equation 4. And Q2 is constant volume. Q2 happens in constant volume process, heat rejection. So it will be, instead of mCp, it will be mCv delta T. And remember here also already we have given a negative sign for Q2. So while writing this expression, Q2 should be in positive value. So it should be mCv T4 minus T1, not T1 minus T4, because you can see T4 is greater than T1. So we can write it as mCv T4 minus T1. Now this is our equation 5. Now just substitute 4 and 5 in 3. So substitute equation 4 and 5 in 3. We will get efficiency is equal to 1 minus Q2. Q2 is mCv T4 minus T1. mCv T4 minus T1 divided by Q1 is mCp T3 minus T2. Now we can cancel this m from this. And what is Cp by Cv? This Cp by Cv is gamma. Ratio of specific heat of particular gas is gamma. So this equation is 1 minus 1 by gamma T4 minus T1 by T3 minus T2. So this is our next equation, that is equation number 6. So now we have obtained an efficiency expression in terms of temperature, but this is not sufficient. Remember in Otto cycle also we have obtained a similar expression. but we have to convert this in terms of volume ratio. In Otto cycle we have converted this in terms of combustion ratio. Now the question is here, how many volume ratios will be there? Here it is not like Otto cycle. If you now go back to the PV diagram, how many volumes are there? Here this yellow line represents one volume and here is one volume, but in between here we have one more volume. So that means here we have three volume levels, hence we will have three volume ratios. So that is why diesel engine is a derivation is a little bit lengthy, because we have three volumes and three volume ratios. So first one we have to define combustion ratio. Combustion ratio is here also the combustion ratio RK. Combustion ratio is RK, that is volume before combustion divided by volume after combustion. What is that? Here volume before combustion, the starting of combustion is V1 and at the end it reaches to V2. So combustion ratio is V1 by V2. So that is same as at Otto cycle, but here remember it is not equal to V4 by V3. In Otto cycle this V1 by V2 was equal to V4 by V3, but here you can see this V2 and V3 are different, hence they are not equal. So combustion ratio is only V1 by V2. The next ratio is the cut-off ratio, because fuel is cut off. Actual engine, the fuel injection will start from 2 and it end up at 3. So the fuel cut-off happens in this second process, actual engine. So that is known as the cut-off ratio. The next ratio is cut-off ratio, that is V3 by V2. So we have RC, let's represent it by RC, that is, so this is combustion ratio, this is cut-off ratio, that is V3 by V2, and finally, so it is V3 by V2, and finally we have expansion ratio also, because here expansion is happening in different volume, that is expansion ratio, it can be written as V4 by V3. So remember all these quantities we are writing as greater than 1, that is why we are going for V4 by V3, not V3 by V4, because V3 is less than V4. So if you are writing expansion ratio like V3 by V4, it will be less than 1. So we have to write it as V4 by V3. So expansion ratio, that is like happening in the this third process, that is V4 by V3. So we have this expansion ratio. Expansion ratio is V4 by V3. So expansion ratio is V4 by V3. So we have another set of equations. We can number it as A, or we can continuously number, or it will be better to number in another way, A, B and C. So these are equations for volume expressions: combustion ratio, cut-off ratio, expansion ratio. But our next question is whether these three are independent quantities, or if you have any relationship between these two or these three ratios. We can simplify that. Suppose if you are some relation between one ratio and other two ratios, you can reduce the number of equations. So for that, if you just multiply B and C, so what will happen if you multiply B into C? That is RC into RE equal to, so in the right side we have V3 by V2 into V4 by V3. So V3 cancels, you can cancel V3, it will be V4 by V2. But what is V4 from this? V4 is same as V1, because you can see here V4 and V1 are on the same volume line. So this V4 we can replace by V1. So ultimately this is V equal to V1 by V2. Now what is V1 by V2? From this it is the compression ratio. So we can say Rk is equal to Rc into Re. So we have obtained another equation which connects these three volume ratios so that we can reduce the equations, and let it be the equation D. So the advantage is we can use only two ratios if possible, not require all the three ratios because they are connected, and mostly in an engine we will be using this compression ratio and cutoff ratio. This expansion ratio is not used widely. Mostly compression ratio and cutoff ratio we will use. So we can obtain all the volume ratios. Now we can think about converting this expression of efficiency into volume ratios. So here we are it's a little bit change comparing to Otto cycle. Here we have to express all the temperatures in terms of T1. So if you are able to express this T2, T3 and T4 in terms of T1, we can very easily cancel T1 from every term and we can express in terms of volume ratio. So for that you take one by one every process you have to consider. Now go for the first process. So first process is consider process 1 to 2 reversible adiabatic process combustion. So here we have two equation. One is P1 V1 raised to gamma is equal to P2 V2 raised to gamma, and another one is ideal gas equation. P1 V1 by T1 is equal to P2 V2 by T2. Now compare this two equation and eliminate pressure so that we can write T2 and T1 in terms of V1 and V2. So already we have done this in Otto cycle. What we have done is you take this equation and we can write T2 by T1 is equal to P2 V2 by P1 V1. Now from what is P2 by P1? From this equation P2 by P1 is V1 by V2 raised to gamma. Substitute that here, V1 by V2 raised to gamma. So we will get T2 by T1 equals V1 by V2 raised to gamma minus 1. But what is this V1 by V2 from equation A? That is the compression ratio Rk. So this is nothing but compression ratio Rk. So we can write T2 equals to T1 Rk raised to gamma minus 1. So this is same as that of Otto cycle. Otto cycle also we have obtained a similar expression. So first we have successfully expressed temperature T2 in terms of T1 by considering process 1 to 2 and combining these two equations. Now this will be our next equation, that is equation 7. So this will be equation 7. Now we have to go for the process 2 to 3. Now consider process 2 to 3. Consider process 2 to 3. Now what are the two equations? So here it is not adiabatic, but you can write the ideal gas equation. It is whole for entire cycle. That is P2 V2 by T2 is equal to P3 V3 by T3. That is ideal gas equation for 2 and 3. And here we know that the pressure is constant. So P2 equals P3. That is the one more equation we have in this process. P2 equal P3. That means you can directly cancel P2 and P3 from here. And what will be the T3 by T2? T3 by T2 will be V3 by V2. So T3 by T2 is V3 by V2. And this volume ratio, what is this volume ratio V3 by V2 from here? This one, it is cutoff ratio. So cutoff ratio RC, V3 by V2. So you can replace this by cutoff ratio RC. So we are getting T3 equals T2 into RC. But remember, we have to express every temperature in terms of T1. Then only we can eliminate temperature from the efficiency expression. Now for that, we have to again convert this T2 in terms of T1. Just use the previous equation, that is equation 7. We have this T2 is equal to T1 RK raised to gamma minus 1. So substitute equation 7. Substitute equation 7 in this. We will be getting T3 equals T1 RC RK raised to gamma minus 1. So this will be our next set of equation connecting temperatures. That is next equation, that will be equation 8. So this is equation 8. So we have expressed T2 in terms of T1, that is T2 is equal to T1 RK raised to gamma minus 1. We have expressed T3 in terms of T1, that is T3 is equal to T1 RC and RK raised to gamma minus 1. Now we have to go for 3 to 4 because we have to express T4 also like this. So consider process 3 to 4, which is again adiabatic process. Remember 1 to 2 and 3 to 4 are adiabatic. So we can write P3 V3 raised to gamma is equal to P4 V4 raised to gamma, adiabatic equation. Then ideal gas equation P3 V3 by T3 is equal to P4 V4 by T4. So this is ideal gas equation, and next one is the adiabatic equation. Now here also combine to this and eliminate pressure. So here we can write it as T3 by T4. What is T3 by T4? T3 by T4 from this equation. T3 by T4 will be P3 V3 divided by P4 V4. P3 V3 divided by P4 V4. Now what is P3 by P4 from this equation, just previous equation? From this equation we will get P3 by P4. What is P3 by P4? P3 by P4 is V4 by V3 raised to gamma. So this is V4 by V3 raised to gamma. Substitute that here. So we are eliminating pressure ratio and substituting just from combining these two equations. So we will get T3 by T4 is equal to, here we have V4 by V3 raised to gamma, and this is V4 by V3 raised to minus 1. So this will be V4 by V3 raised to gamma minus 1. Now what is this ratio? We have one more volume ratio, that will be expansion ratio. V4 by V3 is expansion ratio. So this is equal to Re raised to gamma minus 1. But remember, this expansion ratio are not used in an engine. Normally combustion ratio and cutoff ratio are used. So you got to use this equation. What is expansion ratio? Expansion ratio will be combustion ratio divided by cutoff ratio, RK by RC. That is from equation D. So from equation D, referring equation D, you can write it as T3 by T4 is RK divided by RC all raised to gamma minus 1. Now what will be T4? So we have to express T4. Already we have expressed T3 before. So T4 will be T3 divided by, or T4 will be T3 into RC raised to gamma minus 1 divided by RK raised to gamma minus 1. So we have expressed T4 in terms of T3 and volume ratios. But remember, our aim is to express every temperature in terms of T1. So what we will do? We have to replace this T3 by this. So we have equation 8. T3 is equal to T1 into this. Just substitute that. So equation 8. Substitute equation 8. Substitute equation 8 in the above expression. So what we will get? T4 is equal to, so T3 is nothing but T1 RK raised to gamma minus 1 into RC. So this is our T3, and here we have RC raised to gamma minus 1. Here we have RC raised to gamma minus 1 and RK raised to gamma minus 1. So this RK raised to gamma minus 1 will get cancelled here, and RC into RC raised to gamma minus 1. So finally we are getting T4 is equal to T1 RC raised to gamma. So this is our next equation. So we have successfully completed every temperature in terms of T1. So this will be our equation 9. So refer equation 7, 8 and 9. So maybe we can write it together. That is, equation 7 is T2 is equal to T1 RK raised to gamma minus 1. This is equation 7. Equation 8 is T3 is equal to T1 RC RK raised to gamma minus 1. And equation 9 is T4 is equal to T1 RC raised to gamma. So we have, this is equation 7, 8, 10, and we have successfully expressed every temperature in terms of T1. Now go back to this expression for efficiency and substitute that. So substitute this 7, 8, 10, 9 in 6. Substitute 7, 8 and 9 in equation 6. So that will be efficiency is equal to 1 minus 1 by gamma. Here we have T4 minus T1. So equation 6, this is equation 6. 1 minus 1 by gamma. T4 minus T1 by T3 minus T2. So T4 is T1 RC raised to gamma. T4 minus T1 divided by T3 is this, that is T1 RC RK raised to gamma minus 1 and minus T2. So T2 is again T1 RK raised to gamma minus 1. So here you can see T1 is every term, numerator and denominator we have T1. You can cancel this T1 very easily, so that this efficiency is independent of temperature and contains only compression ratio and the cutoff ratio. And in the denominator you can see here also we have RK raised to gamma minus 1. Here also we have RK raised to gamma minus 1. So we can take it outside for simplicity. So finally our expression for efficiency of diesel cycle will be like this: 1 minus 1 by gamma RC raised to gamma minus 1 divided by RK raised to gamma minus 1 into, here we have RC minus 1. So this is the final expression of efficiency of a diesel cycle. So we have to remember this also, because in problems you may not get sufficient time for derivation. So you have to by heart this equation also for solving problems. And this is our expression. So it contains only two parameters. One is combustion ratio and another one is cutoff ratio, and we have gamma also. So with this we are stopping this diesel cycle. Thank you for watching.